The paper of the day is an overview of query optimization in relational systems. Paper focuses primarily on the optimization of SQL queries in relational database systems and present author's view on the field. The goal of this article is not to be comprehensive, but rather to explain the foundations and present samplings of significant work in this area. Optimization is much more than transformations and query equivalence. The infrastructure for optimization is significant. Designing effective and correct SQL transformations is hard. Developing a robust cost metric is elusive, and building an extensible enumeration architecture is a significant undertaking. Despite many years of work, significant open problems remain. However, an understanding of the existing engineering framework is necessary for making effective contributions to the area of query optimization. Now, query optimizations can be viewed as a difficult search problem. In order to solve this problem, we need to provide first a space of plans, that is the search space. Second, a cost estimation technique so that a cost may be assigned to each plan in the search space. Intuitively, this is an estimation of the resources needed for the execution of the plan. Third, an enumeration algorithm that can search through the execution space. A desirable optimizer is one where the search space include plans that have low cost. The costing technique is accurate and the enumeration algorithm is efficient. Each of these three tasks is non-trivial, and that is why building a good optimizer is an enormous undertaking. Now, the paper presents an example which is a system R optimizer. The cost model assigns an estimated cost to any partial or complete plan in the search space. It also determines the estimated size of the data stream for output of every operator in the plan. It relies on a set of statistics maintained on relationals and indexes. Example, number of data pages in a relation, number of pages in an index, number of distinct values in a column. Formulas to estimate selectivity of predicates and to project the size of output data stream for every operator node. For example, the size of the output of a join is estimated by taking the product of the sizes of the two relations and then applying the join selectively of all applicable predicates. Formulas to estimate the CPU and I/O costs of query execution for every operator. These formulas take into account the statistical properties of its input data streams, existing access methods over the input data streams, and any available order on the data streams. Example, if a data stream is ordered, then the cost of a sort merge join on that stream may be significantly reduced. In addition, it is also checked if the output data stream will have any order. The enumeration algorithm for System R Optimizer demonstrates two important techniques: use of dynamic programming and use of interesting orders. Despite the elegance of System R approach, the framework cannot be easily extended to incorporate other logical transformations, beyond join ordering, that expand the search space. This led to the development of more extensible optimization technique architectures. However, the use of cost-based optimization, dynamic programming, and interesting orders strongly influence subsequent developments in optimizations. Now, let's look at the statistics and cost estimation. Given a query, there are many logically equivalent algebraic expressions, and for each of those expressions, there are many ways to implement them as operators. Even if we ignore the computational complexity of enumerating the space of possibilities, there remains the question of deciding which of the operator trees consumes the least resources. Resources may be CPU time, I/O cost, memory, communication bandwidth, or a combination of these. Therefore, given an operator tree, partial or complete, of a query, being able to accurately and efficiently calculate its cost is of fundamental importance. The cost estimation must be accurate because optimization is only as good as its cost estimates. Cost estimation must be efficient since it is in the inner loop of query optimization and is repeatedly invoked. The basic estimation framework is derived from the System R approach. There are a couple of key points here. Collect statistical summaries of data that has been stored. Second, given an operator and the statistical summary for each of its input data streams, determine the statistical summary of the output data stream, estimate cost of executing the operation. It is important to recognize the differences between the nature of the statistical property and the cost of a plan. The statistical property of the output data stream of a plan is the same as that of any other plan for the same query, but its cost can be different from the other plans. In other words, statistical summary is a logical property, but the cost of a plan is a physical property. An enumeration algorithm must pick an inexpensive execution plan for a given query by exploring the search space. Paper focuses on two representative examples of such extensible optimizers, Starburst and Volcano and Cascades. Despite their differences, they can summarize some of the commonality in them. Use of generalized cost functions and physical properties with operator nodes. Use of rule engine that allows transformations to modify the query expression or the operator trees. Such rule engines also provide the ability to direct search to achieve efficiency. Many exposed knobs that can be used to tune the behavior of the system. Unfortunately, setting these knobs for optimal performance is a daunting task. Now let's talk PS score for this paper. Overall, this paper is a nice and engaging read, so it gets 9 out of 10 on readability. With 10 pages long, it scores 9 out of 10 on length. It's an analysis paper focused on query optimization overview with decent description, so that makes it 9 out of 10. Its industry value and learning meter is pretty good, so it gets 8 out of 10 on each. Overall PS score is 9 out of 10.